Lecture 3, Matter and Energy. Objectives. Learn about matter and its three states. Learn to distinguish between physical and chemical properties. Learn to differentiate between physical and chemical changes. Understand the definitions of elements and compounds. Learn to distinguish between mixtures and pure substances. Learn two methods of separating mixtures. Matter and its changes. Why this matters. All things air, water, food, metals, and our bodies are composed of matter. Chemistry begins by understanding what matter is, how it behaves, and how it changes. 1. Matter and its three states. Definition of matter. Matter is anything that has mass and occupies space. The three common states of matter. Solid, definite shape and volume, ice, metal. Liquid, definite volume, variable shape, water, oil. Gas, no definite shape or volume, air. Key idea. The state of matter depends on particle motion and energy, not on what the substance is. Example. Water can exist as ice, solid. Liquid water. Water vapor, gas. 2. Physical versus chemical properties. Physical properties can be observed without changing the substance's identity. Color, density, melting point, electrical conductivity. Chemical properties describe how a substance reacts or changes into a new substance. Flammability, rusting, reactivity with acids. Example, density of iron physical property. Iron rusting chemical property. 3. Physical versus chemical changes. Physical changes in form or state, not in identity. Melting, freezing, crushing, dissolving sugar in water. Chemical changes produce new substances. Burning, rusting, cooking food, digestion. Key clue. If bonds are broken or formed, a chemical change occurs. For elements and compounds. Element, a pure substance made of one type of atom. Examples, oxygen, O, iron, Fe, carbon, C. Compound, a pure substance made of two or more elements chemically bonded. Examples, water, H2O, carbon dioxide, CO2, sodium chloride, NaCl. Important distinction. Compounds have a fixed composition and exhibit new properties that differ from those of their elements. 5. Pure substances versus mixtures. Pure substances, elements and compounds. Fixed composition. Cannot be separated by physical means. Mixtures, physical combinations of substances. Variable composition. Can be separated physically. Types of mixtures. Homogeneous, uniform, saltwater, air. Heterogeneous, non-uniform, sand plus water. 6. Methods of separating mixtures.
Okay, let me stop into here and let me explain you some things that we have expressed before. First of all, when you're going to the solid to the liquid, this is melting. Ice and water liquid are the same substance, water. So there is no change of the substance, and we are in front of a physical change. Same thing when you go from melting to evaporation. If you go directly from solid to a gas state, is what we call sublimation. When you go from the gas to the liquid, that's condensation. From liquid to solid, freezing. And if you go directly from gas to solid, we are in front of deposition. Then, what is the difference between a physical and a chemical property? Well, physical properties the matter doesn't change, sorry, but in a chemical property or chemical changes, matter changes. For example, flammability, rusting, and reactivity with acids are chemical properties because you have here changes into new substances. So let's go to here. Well, here you have the classification of matter according to pure substances that can be elements. When you have atoms of the same element, like iron, you are in front of an element. But if you have two types of atoms that are joined together by chemical forces, then you are in front of a compound. And when you have mixtures of different compounds, you can distinguish one from the other, then you are in front of a heterogeneous mixture. But if you don't distinguish which one is one of the compound from the other one, then you are in front of homogeneous mixtures. The methods of separations can be, for example, to separate a solid from a liquid, example sand and water, you can use filtration or decantation. And if you have two liquids that the boiling point is different, you can use distillation. For example, in this case, the liquid that has the lowest boiling point will go to the gas phase faster than the other one. And here it will condense and you can get the, first liquid, the one with the lowest boiling point. If you have a mixture of water and alcohol, you can separate alcohol this way and water remains here because the boiling point of alcohol is lower than the boiling point of water. There are other methods like decantation when you have two liquids that cannot be separated, that don't mix. For example, oil and water, they don't mix because one is it's a substance that that is polar and oil is non-polar. They don't mix. Then you can separate them by using a type of funnel. Here you can separate, and the first liquid that you will have down will be water. Then you stop into here, and then you get oil separated from water. This is a method to separate two liquids that cannot be mixed together. Let me continue now with the rest of this lecture. And here we go and we are going to see some tricky questions.
Tricky evaluation style questions. These reflect how students will be tested in this class. Question 1. True or false, a gas is not matter because it has no fixed shape or volume. Answer, false. What is incorrect? Matter requires mass and space, not a fixed shape or volume. Question 2. True or false, color is a chemical property because it helps identify a substance. Answer, false. What is incorrect? Color does not involve a chemical change, it is a physical property. Question 3. True or false, when ice melts, a chemical change occurs because the substance looks different. Answer, false. What is incorrect? Melting changes state, not chemical identity. Question 4. True or false, water is an element because it cannot be separated easily. Answer, false. What is incorrect? Water is a compound made of hydrogen and oxygen. Question 5. True or false, air is a pure substance because it looks uniform. Answer, false. What is incorrect? Air is a homogeneous mixture, not a pure substance. Question 6. True or false, filtration can be used to separate dissolved salt from water. Answer, false. What is incorrect? Dissolved substances require distillation or evaporation, not filtration. Key takeaway for students. In this class, reading carefully matters. Understanding concepts beats memorization. You must justify why something is true or false. Chemistry explains everyday reality.
Okay, I want only to stop into this question that is about the colors. Let's see here. There was a question that asked you about if color is a physical or a chemical property. Let me see if I can see this. It was here. Oh, sorry. Then, well, I don't see it easily, but we have to be very careful when we talk about color. You say, for example, the substance is green. Okay, green. In this case, green is a physical property because describe the color of the substance. But be careful because sometimes you have a green substance and you begin heating this substance, and what happened? Well, that the color changes from green to black. And when there is a change of color, for sure you are in front of a chemical change because the new substance is black. Then there is a change of the type of substance during the change. Sorry to use the word change so many times. Be careful with that, okay? All right, let's continue with this lecture. As you can see, this lecture has chapter 3, but also has chapter 10 in your book. You can find energy, heat, and temperature in lecture in the chapter 10, sorry. But these two parts are in week 3, in lecture 3.
Energy, heat, and temperature. Objectives. Understand the general properties of energy. Understand the concepts of temperature and heat. Consider the direction of energy flow as heat. Understand how energy flow affects internal energy. Understand how heat is measured. Why energy matters. All chemical and physical changes involve energy. Understanding how energy is stored, transferred, and measured allows us to explain temperature changes, chemical reactions, and everyday processes such as heating, cooling, and phase changes. 1. General properties of energy. Definition: energy is the ability to do work or produce heat. Key properties of energy. Energy can be transferred. Energy can be converted from one form to another. Energy is conserved. It is not created or destroyed. Common forms of energy. Kinetic energy, motion. Potential energy, stored energy. Thermal energy, associated with particle motion. Chemical energy, stored in bonds. Example: gasoline stores chemical energy that is converted into kinetic energy when a car moves.
Okay, let me stop into here. You can see in this picture that according with the position of this boy riding this bicycle, you can have potential or kinetic energy. When the boy is going up the mountain, the energy is mainly kinetic because it's related to movement. But when he's in the top of the mountain, the the energy is mainly potential energy because it's a store and depends on the altitude, on the height of this boy. But when he goes down, then this potential energy that he has at this top of the mountain begin, begins converting into a kinetic energy related to the movement. And when he's here in this part of the mountain, once again, the energy is potential. Let's continue then. Remember that energy cannot be created or lost, only can be transferred, can be converted, because energy is conserved, not created, no, or destroyed. Got it? Let's continue then with temperature and heat.
Temperature versus heat. Temperature measures the average kinetic energy of particles, indicates how hot or cold something is, does not depend on the amount of substance. Heat, energy transferred due to a temperature difference, depends on mass, material, and temperature change. Key distinction. Temperature is a measure, heat is a process. Example. A cup of boiling water and a bathtub of warm water may have different temperatures and very different amounts of heat. 3. Direction of energy flow is heat. Fundamental rule. Heat always flows from a higher temperature to a lower temperature. Hot-cold. Never the opposite without external work. Example. A hot coffee cools down in a room. Ice melts in your hand. Important note. Heat flow stops when thermal equilibrium is reached. 4. Energy flow and internal energy. Internal energy and the first law of thermodynamics. Internal energy, U, is the sum of all microscopic energies in a system, motion plus interactions. The way the first law of thermodynamics governs changes. Q equals heat added to the system. W equals work done on the system. This equation explains why internal energy depends not only on heat transfer but also on work. Heat, Q, contribution. If you supply heat, e.g. heating water, molecules move faster, kinetic energy increases delta U0. If heat leaves the system, e.g. cooling gas, molecular motion slows delta U0. Work, W, contribution. Work can also change internal energy, even without heat. Compression of a gas. When you push a piston inward, you do work on the gas. Molecules collide more often and move faster delta U0. Expansion of a gas. If the gas pushes the piston outward, the system does work on the surroundings. Molecules lose energy delta U0.
Okay, lower than zero. Let me stop into here because there is something important that I want you to understand. First of all, internal energy is equal, as we can see before, to Q and W. What is Q and what is W? Well, as you can see before, Q is the heat added to the system, and W is the work done on the system. So the internal energy depends on both, on heat and work. If you're heating water on a stove, what will happen? That Q will increase. Q will go up. Q will go up. So what will happen to the internal energy? What will happen to the internal energy? Also will improve. If you are compressing air in your bicycle pump, well, Q remains constant. But you're doing work. So delta energy in this case increases because of work. If this increases because the work increases too. If you're letting a gas to expand freely without doing work, no work, then the internal energy decreases. Let's see, let's go and let's continue with our lecture.
Key insight. Internal energy is a state function. It depends only on the system's state, not on the path. But the way it changes depends on two pathways. Heat transfer, Q. Work, W. That's why we say, U depends on Q and W. They are the mechanisms by which energy flows in or out, altering the system's internal energy. It shows a piston with gas inside a cylinder, illustrating both compression, work done on the gas, increasing internal energy, and expansion, work done by the gas, decreasing internal energy, along with arrows for heat, Q, and work, W, to make clear how they affect the internal energy, U.
Okay, let's stop into here because in this graph, you can see how when, when you are compressing or you are expanding, then what will happen? If you're heating, what will happen? Then the internal energy will be higher than zero because Q is higher than zero. In the expansion, without work, okay, in this case, the internal energy is negative because the work is also negative. It's an expansion, a free expansion. You are not doing work on the system. The system is doing the work against the environment. Let's see then. Measuring heat. The units of heat are joule in the international system, or calorie, that is an old unit. 1 calorie is equal to 4.184 joules. This conversion is very important. You can have a question asking to convert a certain amount of calories into joule, then you have to use the dimensional analysis that I showed you in the last lecture to convert calories into joule. Also, using a calorimetry or using calorimetry, you can measure the change of the amount of heat in a system. If you know that Q, that is the heat in joule, is equal to the mass times the specific heat, that is C. C is the specific heat times the change of temperature, final temperature minus initial temperature, that is delta T. You can calculate the amount of heat that is produced. For example, let me show you something that is very, very important.
Water has a high specific heat, which is why oceans moderate the climate. Why the Earth's temperature changes little despite large energy from the sun. Although the Earth receives a vast amount of energy from the sun, its temperature does not change dramatically. This is because substances like water have a high specific heat, meaning they can absorb and store large amounts of energy without experiencing a significant temperature rise. Oceans, which cover much of the Earth's surface, play a key role in moderating the climate by absorbing solar energy and slowly releasing it. As a result, the temperature on Earth remains relatively stable, even as the planet receives constant energy from the sun. Tricky evaluation style questions. These reflect how exams and quizzes will work in this class. Question 1. True or false, energy can be created when a chemical reaction releases heat. Answer, false. What is incorrect? Energy is transformed, not created. Question 2. True or false, temperature measures the total amount of heat in a substance. Answer, false. What is incorrect? Temperature measures average particle motion, not total heat. Question 3. True or false, if two objects have the same temperature, no heat can flow between them. Answer, true. Why? It's correct. Heat flows only when there is a temperature difference. Question 4. True or false, a large block of ice at 0 degrees Celsius contains less energy than a small cup of water at 0 degrees Celsius. Answer, false. What is incorrect? Internal energy depends on the amount of substance, not just temperature. Question 5. True or false, when heat flows out of a system, the system's internal energy increases. Answer, false. What is incorrect? Losing heat decreases internal energy. Question 6. True or false, heat and temperature are interchangeable terms. Answer, false. What is incorrect? Heat is energy transfer, temperature is a measurement. Conclusions. Heavy checkmark energy is conserved. Heavy checkmark temperature is not equal to heat. Heavy checkmark heat flows in one direction. Heavy checkmark internal energy depends on both motion and quantity. Heavy checkmark units and definitions matter.
Okay, then remember, these are the conclusions for this. Energy is conserved, not created nor destroyed. Temperature is different from heat. Temperature is what you measure. Heat is energy. Heat flows in one direction. Yes, heat flows from hot bodies to cold bodies. Internal energy depends on both motion and quantity. True. And which one are the units and definitions of matter? Matter, first of all, matter is everything that exists. It occupies a volume and weight. Yeah, that's why when I ask you, does a rate of light is matter, then you have to say no, because it has no mass and it doesn't occupy a space, so it is not matter. Well, this is what we have. Please stop the video and read it and watch it several times until you understand. Take notes in your notebooks And if you continue having questions, don't hesitate. Send me an email and we can meet via WebEx. See you in the last lecture.